In this second part of chapter 4 about acid and base, we will talk about the carbonic acid system, or the CO2-H2O system if you prefer. It is a very important system. We'll see that in the following lecture when we'll talk about the buffering capacity of certain elements. Buffering is an action of resisting or fighting against a change in pH. In our case, you can buffer a lot of things, but most of the time when we're talking about buffer, we're talking about acid or base. And we'll see that the carbonate system is a very important component that is fighting against pH change in natural environments. Why you want to fight against pH change? We saw that rapidly life is like neutral or close to neutral pH. It doesn't like huge shift in pH. You know that acid water or very alkaline water or basic water is not very good for our system. Also, if you're dealing with the lithosphere and you are interested in the carbon cycling, one important side of the carbon cycling is the inorganic carbon, is mostly what is the carbon that is dissolved into the water. And some of this carbon will be found under the form of what we call limestone. Limestones are sedimentary rock composed mostly of calcium carbonate, which is calcium plus some carbonate, anion. You can have other cation, of course. You can have a lot of different carbonate, but the most frequent, abundant carbonate on the planet is the calcium carbonate, the limestone. Where is this carbonate coming from? We have a hint already. We talked about that in previous lecture. It's coming from the dissolution of CO2 into the water. It just happened that all gas are able to be dissolved into water. And if you have some water here, you can dissolve a certain amount of gas inside your water. In this case, it's going to be CO2. So again, any gas can be partially dissolved in water. Oxygen, nitrogen, you name it, methane. It just happened that CO2 have a strong affinity with water. Why? Because it will interact with water. If you put oxygen into the water, the oxygen will find itself as gas surrounded by water molecule. Remember this famous water molecule with the H2O, the 2H, and the polar structure will be attracted to the negative side of the oxygen atom. So you will have a molecule of O2 surrounded by water, and they will stay like that. You will not interact, you will not create additional component with this gas mixed with water. CO2 is slightly different because CO2, that is under the form of gas, plus water, will give you CO2 aqueous inside the water. We can simplify by removing water on each side. That will give you just a reaction of CO2 as a gas that can dissolve into water and turn into CO2 aqueous. And we can write the equilibrium constant for this reaction, which is equal to the concentration of CO2 aqueous divided by the concentration of CO2 as a gas in the atmosphere above the liquid. So this can be seen as a relationship between the pressure, the partial pressure of a gas that is in contact with a body of water and the amount of this gas that can be dissolved into the water. So if you have here an atmosphere with a PCO2, a partial pressure of CO2, this partial pressure of CO2 will be proportional to the amount of this CO2 that can be dissolved into the water. And the coefficient of proportionality will be this K, this constant of equilibrium, that can also be called a solubility constant. Solubility constant. Same formula, different name. Solubility constant is how much of this gas can be dissolved into the water. And this constant can be different, of course, will be different for different gases. This solubility constant can also be called Henry's constant. Henry's constant. This is coming from a law called the Henry's law that was defined way before the modern chemistry, if you want. All this definition of a solubility constant or equilibrium constant, thermodynamics. A scientist called Henry put this rule together so that the amount of gas that you can dissolve into water is related to the partial pressure of this gas in contact with this liquid. So you can rearrange this equation here by having the amount of CO2 that can be dissolved into a body of water is proportional to the PCO2 in our case time a constant. The Henry's constant in our case, this is the solubility constant or equilibrium constant, that's the same. And this is the Henry's law. You have to be careful because this Henry's constant here, as we define it this way, is related to the solubility of the gas within a liquid. But some other scientists have defined the Henry's law before this solubility constant theory, and we're talking about the actually escaping of a gas out of a system. Meaning you have a certain amount of CO2 here, and part of the CO2 can escape, or the volatilization of a gas. And this, we have a constant of, we call that V for volatilization, right? And so this is basically the opposite way as a solubility. You're not interested in how much gas you're putting into your liquid. You are interested as how much gas will leave the liquid. And so this is why you will see in the literature the Kv, which is the volatilization constant, will be equal to 1 on our case K CO2. So it's just for you to realize that when you're reading a paper in literature that deal with Henry's law, with the dissolution of specific gas, specifically CO2, be careful to the unit of the constant of Henry's constant. Sometimes you can have a big number, sometimes you can have a small number. That is often the same constant for the gas. The difference is one is seen as a solubility product or solubility constant, and another one will be equal to 1 on this solubility constant. Again, this is very important. Read the unit associated to the Henry's constant. That means you can have a different value for the same gas following the different definitions. So CO2 as a gas can be dissolved into water and form CO2 aqueous. And then the next step would be to have the combination of this aqueous CO2 with water. That means that it's not only a molecule of CO2 with some molecule of water surrounded this molecule here, in this case. This is molecule of water, if you remember that. Okay, surrounded by molecule of water. But in this case, you have the combination of CO2 plus H2O, giving you H2CO3. And we have seen this. It is what we call the carbonic acid. It is important to understand that CO2 as a gas, when dissolved into water, will be found as two different species, the CO2 aqueous and the dissociated CO2 with water. And those two are two different components. But as it is very difficult to to measure the difference, what part of this CO2 is under the form of a gas surrounded by water or a dissociated carbonic acid, we're grouping all of that into a generic term called H2CO3 with a star. So when you're writing this with a star, that means this is equal to the aqueous CO2 plus the real carbonic acid. If you want, you can write it this way, the H2CO3 0, which is the real carbonic acid. Not this is this, okay? So this is KCO2, we have seen that, equal the activity of CO2, aqueous, divided by the PCO2. And this is the solubility of CO2, or also called the Henry's constant. And value for the Henry's constant are given in this table here, for example. And you see for CO2, this is this column. You can see that this value is pretty high compared to value such as oxygen or nitrogen. So you can put way more CO2 into water than the oxygen or nitrogen. Those two gases have a strong affinity for water. Interestingly also is, as this number you see decrease with temperature, okay, you can see that this trend is increasing with lower temperature. That means the CO2, you can put more CO2 into a cold body of water than a warm body of water. What is the take-home message here is that the KCO2 is depending on the temperature and pressure. If you have low temperature, you can put more CO2. If you have high pressure, you can put more CO2. You understand that? Because it's proportional. If the PCO2 is higher, you can put more CO2 in the water. If the temperature is lower, so you can put a lot more CO2. This concept explains why in groundwater, in the lithosphere, at cooler temperature, higher pressure, can actually dissolve more CO2 in the water. That's a concept we will use a little bit later in another lecture. We have this value at 25 degrees C is 3.39 times 10 to the power of minus 2, which is exactly the same number as this number here. If you compute that in your calculator, you will see that you will find exactly this number here, the 3.39 10 to the power of minus 2. So this is the first value for the solubility of CO2 into the water. But the carbonic acid is a weak acid. We have seen that before. Now we know how to deal with polyprotic weak acid. Again, this is a polyprotic. There are more than one proton in this acid, and they will dissociate in sequence as any diprotic acid. And for each reaction, you will have a different pKa1, pKa2. So the carbonic acid, in this case, both CO2 and aqueous CO2 and carbonic acid, plus water, will give you the famous HCO3 minus plus H3O plus, hydronium in this case. And this is what we call the bicarbonate. And this is some acidity, of course, and with a specific Ka1 equal 10 to the power of minus 6.5. That means that in this case you can write that down as the Ka1 equal the concentration of bicarbonate times the concentration of H plus, I will simplify hydronium as H plus, divided by the concentration of carbonic acid. the water is 0 in this case. And this is equal to 10 minus 6.5. As we know now, as a specific temperature, room temperature of 25 degrees C and a pressure of 1 atmosphere. This is very, very important. We have seen that for the pH already. The pH, the neutral pH change as a function of the temperature. So this value will also change as a function of the temperature and the pressure. Then, this is the first equation. The second one would be the bicarbonate will then dissociate. I will forget about the water in this case. Will give you carbonate ion plus H plus. And this famous carbonate you need to precipitate calcium carbonate, for example, with a Ka2 equal to the concentration of carbonate times the concentration of H plus divided by the concentration of bicarbonate. And this Ka2 is equal to 10 power of minus 10.5 at 25 degrees C and 1 atmosphere. So this is a summary of what will happen with this carbonic acid. So this is, with the better writing, what I just wrote, and you see that I rounded those numbers, and the real number is 10 to the power of minus 6.35 for Ka1 here, and Ka2 is around 10.33. That means that the pKa1 equal 6.35 and the pKa2 equal 10.33, again at temperature of 25 degrees C and 1 atmosphere. So that allows you to make some calculation to try to calculate how much CO2 is dissolved into water and what different species can be found inside your body of water. The first exercise you can actually do is try to calculate the pH of the rainwater in equilibrium with the atmospheric CO2. So for doing that, you can actually do that with me right now. We're going to do this exercise. We know that the PCO2 is equal to 10 to the power of minus 3.5 atmosphere, which is equal to 35 ppm ppmv. Actually, those are all the value now. You may be aware that this CO2 concentration or partial pressure is increasing lately due to human activity, and this value is more or less around 400 now, ppmv. ppmv is part per million per volume. For gas, you're always putting volume because you will need to have some kind of reference to a certain volume. So, but it's per million, the same as 10 to the minus 3.5 atmosphere. That is the value for the PCO2. And we have seen that the Henry's law, which is the KCO2, equal 10 to the power of minus 1.47. We just saw that here. This is this famous calculation here. I rounded, it's 46 actually. 46 here. This is the initial value. So from those two values, you can use this first initial calculation here. Okay, this to calculate how much carbonic acid you are in your rainwater. So in this case, what you have here is the KCO2 equal the concentration of H2CO3 divided by the PCO2. So that means that the concentration of H2CO3 star equal KCO2 times the PCO2. This value is equal to 10 to the power of minus 4.92, which is this number plus this number. So now the next step is to calculate the pH. you're on the pH of the water. So the pH of water, again, pH is equal to minus log of the activity of H+. To have this activity of H+ here, you need a second equation. You need to have this one here, Ka1. Now you have this value you just calculated. So what you're going to do is having the Ka1 equal, calculated before, the H+ concentration of HCO3 minus divided by the carbonic acid concentration in your water. This is the Ka you have here, okay? This is exactly this. So now you're rearranging that by writing H+ times HCO3 minus equal Ka1 that you know time the value H2CO3 minus your concentration of carbonic acid you just calculated here. So you have those numbers. Now the trick is the H+ here, you think that this is pure water. Rainwater as pure water. So the pure water, the pH of the pure water would be 7. That means the 7 is neutral pH. That means the pH equal the pOH. That means the only increase in H+ concentration you will have will come from the dissociation of the carbonic acid. You don't have any other component, just the carbonic acid and water. So the dissociation of water is giving you the neutral pH, and you're adding H+ from the dissociation of the carbonic acid. So every H+ that you're creating will come from 1 mole of carbonic acid. So for every mole of carbonic acid, you will produce 1 mole of H+ and 1 mole of bicarbonate. Though those two numbers are the same. So if you want H+ equal the concentration of bicarbonate, because the only source of H+ is the dissociation of the carbonic acid. That means that H+ square equal Ka1 times the carbonic acid. This is equal to 10 to the power of minus 11.32, and if you're taking the square root of that, you have a result of 10 to the power of minus 0.66. So this is the amount of H+ in solution. The pH is the minus log of that, and the minus log of that is the pH will be equal to 5.66. If you remember, the neutral pH is 7. That means that the rainwater is slightly acidic because of the incorporation or dissolution of CO2 into the water. So rainwater is slightly acidic.